I think we're going to do extreme summarization. Yeah, let's go ahead and do that so you can see. So I'm going to work on NSVEC and make it a little bigger. And now we're going to do it like we did last week and do everything in a Python notebook instead of a Jupyter or Python IPython session. Okay, so from index from NSVEC indexers, import index, and we'll create a 200,000 word or 100,000 word index of some nest vectors from FastText. Turns out these are the exact same vectors that was used by the latest and greatest Turing competition winner. The latest Turing competition, well, it's not really a Turing competition, but the latest, the best, most intelligent chatbot that we found so far, at least at the end of 2021, was part of the social bot challenge, and they used FastText vectors, which are the ones that we're using here. So let's get those loaded. I could call it something a little more descriptive, like FT vectors or something. You can tell it the numvex you want. I think it's set, the default is 100,000. Maybe we'll make it a little bigger. Doesn't seem to take too long when we do 100,000. So we'll do 200,000, so it'll be more likely to have rare words like, and Chaudet. And then we're going to do some extreme summarization. What that means is compressing a sentence down to a single word. And we're going to do it on the chapters of the book so we can find the location in the book to insert a new sentence. The idea is we want to find a semantic similarity between sentences, and we need to create this embedding. Let's see. So here's an example. If you put hello and goodbye as the three words in a sentence that you'd like to extremely summarize, which word do you think it's going to come back with? After this takes a few seconds, so you got about 2 more seconds.
Goodbye.
Okay, you think goodbye is more powerful than hello? We're going to see. If you had to summarize this in one sentence, I think that's probably the human way of summarizing it. Actually, hello seems to have a slightly more power. Let's dig in and see if we can figure out what the actual math of what's happening here. So let's do, welcome. Let's see. So the way we do, so I've done a lot of work since y'all were here last to create the index so that it actually, you can look up things by words, or you can look up a vector by its position. So does anybody remember what the most common token is in the FastText word vector? So that these are ranked in order of popularity. So this should be the very top one. If you had to, I think it should be comma. You got it. Oops, we don't get to see what vector that is. So we'll have to do something like index.query. We'll find all the closest vectors. I'm going to query series, so it'll return a series. This takes a vector in order to get out the output, and you're right. So the closest one, which has a distance of 0, essentially, is comma to that vector. So anyway, you can use the index to grab a word, the vector for a word, or a vector for a position in this 200,000 long matrix. Next, we want to, so now we're going to get the vectors for hello, and we're going to add that to the vector for goodbye. We're just going to do hello and goodbye just to make the math a little simpler. That gives us a new vector.
You missed the E in goodbye.
It says it can't find it in our vocabulary. That's interesting. Not sure why it took so long to not find it, but thank you for the correction. And so let's take the average of those vectors. That's I saw in the paper that's what they did for the FastText vectors that they used in this bot called social bot. I forget his name. Matko, I think. Matke is his last name. And Peter, P-E-T-R, without an E in his name. Let's see if Peter's in the FastText. That Petra sort of spelling of Peter is in there. Anyway, this is the author of the paper and the main architect. He's a PhD student who created this chatbot that is the world leader for an entertaining, intelligent conversation that maintains context and continuity in the conversation. This is part of the 2021 Social Bot Challenge. I'm not going to say the big tech corporation that sponsors that, but you can guess. I posted it also on the Carry channel, the information about that. So Peter's not in there. Peter probably is. There we go. Let's go back to our vector average. So we got a vector average now. We're going to call that, we'll just call that av just to make it easy. So now we've still got that av vector here. We can do a query on those words for that av. So we're going to do index.query, just like we did before. Let's see what happens if I don't do the query series, see what it returns. Okay, it returns the old-fashioned query that the index does, that the index, the PYN descent index returns. So that's what that's the derivative of this index class. Just to, that's not going to help. Index. So this is the class that we talked about last week, and what's inside of it. We'll do, maybe I'll do index query, question mark to actually look at the source code so I don't have to go find it. So you can see that it's derived from the PYNN descent package. I just shortened it to PYNN during the import. And this NN descent index that it creates, and it has we're derived from there. So we have all the attributes and methods of the original index, and that's what query does. And I've just added this query series to make it a little more useful and interesting so that we get a list of words. Whoa, if we had just used the raw average, it looks like we would have come up with goodbye rather than hello as being the closest word to the average, though they're both neck and neck here. This is interesting. So Kamal should have been right. Let's see what the math actually did in order for this to happen. Let's try, from np.linalg, let's first import numpy as np. So np.linalg, the linear algebra, has a function called norm that makes it really easy to calculate the norm of something. So this vector is too long because we've added two vectors that have an average of, they're just a normally distributed set of values for these two vectors that we added together. I should have created V1 and V2 so we could go look back at them and see what their norm was. But I think this is the problem with this av vector and why we're coming up with a slightly different answer than what I did within the summarizer. So let's do that. We're going to normalize these vectors, the vector average at least, not only by dividing by 2, because there are two vectors that were added together, but also just making sure that they have unit length each. So they're only moving 1 away from the norm. So this should get us, query series, because I don't like that one. Still goodbye at the top of the list. And okay, so that's not what let's dig in then. Let's see what the actual algorithm is doing. Or maybe we need to add goodbye to it. Let's go all the way back to what we actually did. We'll put these together. And if somebody has a more engaging example that we can use in the book, something related to natural language processing or pro-social behavior or AI ethics, give me a short phrase or sentence that we could use in the book, and we'll start using that instead of hello and goodbye, which is not super interesting. Let's try, this is one other option for what it's doing, that it's doing the norm before it adds them together. V1 divided by the average of V1. There we go, like that. Plus V2 divided by np.linalg. I should just create a norm function from the import, but Still no good joy. And let's just add in the word and. I could actually just name these vectors for and. No, I can't because that's a built-in keyword. So we'll call it v3 equals. And by the way, the order doesn't matter because and now let's add in the at plus v3 divided by np dot linalg dot more v3. And then once this fails, we'll give up and go back to the okay, so this must be the out. So the and word is messing it up. Let's see if it happens. We'll also whether or not we normalize it or not, and whether or not we divide it by 3. So if we just do the sum without dividing by 3, and we include all 3 words, then it's giving us the answer that so this must be the algorithm that I implemented inside. I'm not sure whether I normalized or not, but obviously, well, I may not have divided by 3, but let's see if that changes anything. Okay, good. So it's just the fact that the word and wasn't in the list. Somehow and is kind of a vanilla word, and it's more positive than negative, so maybe more aligned with goodbye, hello, so pushing the vector total out towards hello rather than goodbye. And is kind of an affirmative, and I don't know, whatever. This is not very helpful to readers of the book, this example, because it's very unclear what's actually going on. Let's try something else. Let's look at an actual sentence from the book, because this is what's going to happen towards the end of the chapter. Yeah, let's go ahead and do that. And let's see the actual algorithm for extreme summarize. It's getting the nearest for the nearest vectors, which is that query summarize. For the doc vector, let's see how doc vector is doing it. The doc get doc vector. See, the issue with doing this extreme summarization is you've got to iterate through all of the words in that thing and deal with gracefully with any of the words that don't exist in your vocabulary as you're creating these. So I'm using the dot get method. The dot get method is a method of this actual self object, the index. And so within that, I've created some graceful handling of tokens that don't exist. So like if I say index.get smorgasbord or schmutz, words that likely don't exist there. Oh no, I didn't do it as gracefully as I wanted to. Index object has no attribute OOV vocab. I misspelled something in the code. That's why I didn't fail gracefully. So I find OOV vocab. I intended that's a poor choice of names. When out of vocab is let's see if there's any more misspellings like that, so I can refactor them. Okay, cool. I'd have to exit and get restarted to fix that. But anyway, somehow it worked. Oh, it worked because there were no out of vocabulary words in that phrase that we gave it. So if we give it a sentence that has some odd words in it, we're going to have to deal with that bug and reload the package. But it looks like I just fixed it. That's what mob programming is for. Since I wasn't able to demonstrate that feature, we're going to go to demonstrate what this extreme summarization does on a real sentence from the book. So let's go to the word embeddings are vectors we use to represent the meanings of words. What do y'all think the extreme summarization of that is going to be? I wonder if embeddings or some of these other words are in that thing. So sent equals. By the way, ENO, with this the Spacey package, have you found how to segment text into sentences so you get individual sentences instead of the entire document? Or have you started playing with that Spacey package .sentences thing?
Yeah, I'm still trying to figure it out. So
I'll give you a hint. It's .sense rather than .sentences. When you're looking for sentences out of Spacey. Next, let's go to word embeddings.
I think the summary is vectors.
All right. Sorry, what was that, Kamal?
I think the summary is vectors. Just a guess. Because when you say something is or something are, I mean, the summary should be, because it is kind of assertive, no? Like,
Yeah, yeah, I hear you. You have to feel. Don't forget. You need to think about this sentence being shuffled. It doesn't matter the order of the words. The words aren't associated with each other. They're not being read by a human. They're being read by a machine. And so they're being read out of order. But that's interesting. I'm going to guess word, since the capitalized word and lowercase word are both there. I'm guessing that the word will dominate because there's two words and there's only one of all the other words. Or maybe, I think that's true. We're going to find out. Do you have a guess, Iano? We have a guess for vector. Vectors and embeddings are kind of similar, so maybe you're right there. And representations, those three might gang up and beat word. We're going to find out. Extreme, summarize, sentence, or sent, called it. This is the problem with word vectors. Because it's averaging together all the meanings of all the words, it tends to fuzzy up the meaning and congeal it down to the most generic word it can find. And not necessarily a word that's actually, it is a word in the sentence. That's interesting. I wonder if that's always the case. I wonder if we could ever get it to go to a word that's not in the sentence. This is a really weird property of high dimensional vectors. Their math isn't quite like you would expect it. You have to imagine all these vectors on a tiny, thin little shell. They're all slightly different dimensions, slightly different length. But they're all out there at about a unit sphere, a sphere that's about one length radius. That means that the distance between them is words that are basically all the words are very far apart. And the only way to measure distances is with angle, basically, in this high dimensional space. I think there's a pretty good explanation of that in the book. So this is the problem with extreme summarization. So we may want to try to figure out if we can come up with a better strategy for composing word vectors from or finding the most important word in a sentence rather than doing the average of the word vectors. I can't think of any good ways. Perhaps we can mess with the math of that function that we just looked at, in terms of taking that average or somehow allowing the length to be in the resultant, not worrying about taking the norm. I don't think we had that. I don't think that changed anything when we didn't even do the norm. So that's probably not going to help. What this is telling us is that we're going to end up with some really poor representations of the meaning of sentences if we rely on word vecs. And this is exactly what they found in the social bot challenge when they tried to use fast text vectors and the average vector to represent the meaning of sentences.